Recall that factoring an integer was simply expressing that integer as a product of simpler numbers. So for instance, 12 can be expressed as 4 times 3, which can be further expressed as 2 times 2 times 3. So here I've factored 12 into its two factors 4 and 3, and then I've further factored 4 into 2 times 2. So 12 has been completely factored as 2 times 2 times 3. 2, 2 and 3 are called the factors or divisors of 12. And 12 has been written as a product of factors. In this lesson, we will look at the factorization of algebraic expressions. We will try to express algebraic expressions as a product of simpler factors. Those will also be algebraic expressions. But first, let's look at a fundamental property of multiplication and addition. It's called the distributive property. We're all familiar with it, but just let's formally understand it. So for instance, if I want to multiply 3 times 4 plus 2, there are two ways to go about it. Since there are brackets, I can first simplify within the bracket and write it as 3 times 6, which becomes 18. Or I can use what is called the distributive property and break it up into 3 times 4 plus 3 times 2. So I've distributed the multiplication across the addition. It was 3 times 4 plus 2. I've made it 3 times 4 plus 3 times 2. And now this becomes 12 plus 6 equal to 18. When it's written like this, implicitly you have to do the multiplications first and then the addition, because multiplication has higher priority over addition in the order of operations. Let's look at another example. Minus 2 times 4 plus 7. Here the minus 2 will distribute across the addition, so it will become minus 2 times 4 plus minus 2 times 7. Notice that the minus 2 is multiplied into both the numbers in the brackets, so it becomes minus 8 plus minus 14, which is minus 22. So the distributive property works like this. A times B plus C is A times B plus A times C. What if I have a minus sign within the brackets? So suppose it's A times B minus C. Well, I can write the B minus C as A times B plus minus C. And then I distribute. So I get A times B plus A times minus C, which is AB minus AC. So that multiplication distributes not only across the plus, it also distributes across the minus. A times B minus C is AB minus AC. This is very useful to know. Let's look at an example. 3 times 7 minus 2 can be written as 3 times 7 minus 3 times 2, which is 21 minus 6, which is 15. As can be verified here, 3 times 5 equal to 15. What if there's a minus sign outside? What if it's minus 4 plus 6? Well, we know that's minus 10. Let's see how it works. The minus sign outside can be interpreted as minus 1 times 4 plus 6. And then I distribute it. So it becomes minus 1 times 4 plus minus 1 times 6, which is minus 4 plus minus 6, which is minus 10. So the minus sign gets distributed because the minus sign is simply multiplying by minus 1. So I distribute it across all terms in the brackets. This is an important example because often students are confused with the minus sign outside the brackets. Let's look at one more simple example. Minus 3 plus 7. So again, it's minus 1 distributed across minus 3 plus 7. So that becomes minus 1 times minus 3 plus minus 1 times 7. Minus 1 times minus 3 is 3. plus minus 1 times 7 is minus 7, which becomes 3 plus minus 7, which is minus 4. Let's check it here. Minus, in brackets, minus 3 plus 7, which is 4. Minus times 4 gives me minus 4. We shall use the distributive property not for integers but for algebraic expressions. Find a and b if x square minus ax plus 12 is equal to x minus b into x plus 3. Okay, so this is a quadratic expression. We have powers of x from 2, 1 and 0. Remember that x is the variable here and a and b are constants. So a and b are numbers which we have to find out. Using the distributive property, I shall expand the right hand side. X minus b into x plus 3. This will play the role of a. It will become x minus b into x plus x minus b into 3. Now I can use the distributive property again. X is being distributed across x minus b. So that becomes x into x minus x into b. And here 3 is being distributed across x minus b. So that becomes 3 into x minus 3 into b. Now I group like terms. Firstly, I write x into x as x square. And then I have two terms in x. So I can take x common plus x and I get minus b plus 3. And then I have 3b, which is a constant. So writing it as a quadratic, I get x square plus 3 minus bx. Minus b plus 3 can be written as 3 minus b. And minus 3b. Okay, now we have it written as the quadratic. So I can compare the two quadratics. The left hand side was x square minus ax plus 12. And the right hand side is the expression I've just derived. For two quadratics to be equal, every coefficient of every term of x should be equal. So here we have x square and x square. So that's safe. Here we have a minus a and we have a 3 minus b. So I know that minus a should equal 3 minus b because the coefficients of x on both sides must be equal. The term in x can only equal the term in x. Recall that terms with different powers of x have nothing to do with each other. So the term in x can only be compared with the term in x. And finally the constant term. That's 12 on the left hand side and minus 3b on the right hand side. So they must be equal. Well, this can be solved. I divide by minus 3 on both sides. So I get minus 4 equal to b. I substitute minus 4 for b in the first equation. And I get minus a is equal to 3 minus 4, which is equal to 7. So a is equal to minus 7. And I have my unknowns a and b. Let's check if it makes sense. So it's x square minus 7x plus 12. And on the other side, it's x minus b into x plus 3. So that works out to x square plus 7x plus 12 must equal x plus 4 into x plus 3. You can easily verify if this is right or not by just multiplying out x plus 4 and x plus 3 using the distributive property. And you will get x square plus 7x plus 12. So our solution is right. A is minus 7 and b is minus 4. Factoring the difference of two squares. So I'm sure everyone knows this. What is x square minus y square equal to? Well, it's equal to x plus y into x minus y. Let's prove it. So I am going to multiply x plus y and x minus y. X plus y into x minus y. So I'm going to use the distributive property that I just introduced. So I'm going to do this whole bracket x plus y into x minus this whole bracket x plus y into y. Now I can distribute again. This becomes x into x plus y into x minus, I open a bracket, x into y plus y into y. Here I have distributed y across x plus y. So this becomes x square plus y into x is the same as x into y minus xy minus y square. Remember there's a minus outside the bracket, so it becomes minus y square. The xy's cancel and this becomes x square minus y square as we wanted. So most important formula, x square minus y square is x plus y into x minus y. So this is a difference of two squares and we've written it as a product of two numbers. So we have factored this expression as a product of two binomial expressions. Expression 1, expression 2. Let's apply it. A square minus 25. So a square is clearly x square, 25 should be y square. So I rewrite this as a square minus 5 square. Now it's looking like x square minus y square. So it should end up being a plus 5 into a minus 5. The listener is invited to check this by opening out the two brackets, multiplying them out using the distributive property and ending up with a square minus 5 square. Similarly here, we have x4 minus y6. So what's my x and what's my y to apply this, to apply x square minus y square? So I need to write it as a difference of squares. So I'll write it as x square the whole square minus y cube the whole square. Now I have it as a difference of squares. x4 was written as x square square. Y raised to 6 was written as y cube square. So this becomes x square minus y cube into x square plus y cube. How about this? Again, I got to write it as a difference of squares. So I'll write it as x4 raised to 2 minus y4 raised to 2. So this becomes x raised to 4 plus y raised to 4 into x raised to 4 minus y raised to 4. This is interesting. Here again, this can be written as a difference of squares. So this can be written as x square square minus y square square. So this can go as x square plus y square into x square minus y square. And what's even more interesting, this can go further as x plus y into x minus y. Thank God it's over now. So the entire expression x raised to 8 minus y raised to 8 is x raised to 4 plus y raised to 4 into x raised to 2 plus y raised to 2 into x plus y into x minus y. It's x4 plus y4 into x square plus y square into x plus y into x minus y. I've repeatedly used the difference of two squares. I've used it thrice. How about this? Well, 18 isn't a square, nor is 2z square. So what do I do? Well, I can pull out 2 common. That's what I'm going to do. I'm going to pull out 2 common. Then I get 9 minus z square. Now I'm in business because 9 minus z square is a difference of two squares. It's 3 square minus z square. So this becomes 2, which was pulled out common, into 3 plus z into 3 minus z. I sincerely apologize for my writing skills. They're terrible. So I got 18 minus 2z square, pulled out 2 common, then it was a difference of squares. How about here? Well, again, 4x y raised to 7 is clearly not a square because it's y raised to 7. And I have 25x raised to 5y cube. So I'll try to pull out some x and y's common, and hopefully what I'm left with will be a difference of squares. So I can pull out x common from both, and I can pull out y cube common from both. And what I'm left with is 4y raised to 6 minus 25x raised to 4. And now these are difference of squares. 4y raised to 6 can be written as 2y cubed the whole square. And 25x raised to 4 can be written as 5x square the whole square. X, y cube hanging around outside. Now just complete it by using a difference of squares here. You'll get 2y cube plus 5x square into 2y cube minus 5x square. And you get the entire expression as a product of different factors. X square minus y square is used all the time, but as you can see in these examples, sometimes you have to do some work before you can get your difference of two squares. Here we pulled out 2, here we actually pulled out xy cube. So one has to be adept in noticing what we can pull out. The other two very important formulae are x square minus 2xy plus y square and x square plus 2xy plus y square. These are called perfect square trinomials, and you'll just see why. So let me give you the answer. This is x minus y the whole square. That's why it's called a perfect square trinomial. It ends up being a perfect square. How do we test it? Let's open this out. So this is x minus y into x minus y. I distribute, so it goes x minus y into x minus x minus y into y. This becomes x square minus yx, and put a bracket because of a minus sign. This becomes xy minus y square. Open out the minus sign as x square. Yx will always be written as xy minus xy. Minus and minus gives me plus y square. So what I'm ending up with is x square. Then there are two like terms. Both are minus xy. So that's minus 2xy plus y square, which is what we started with. So x square minus 2xy plus y square factors as x minus y into x minus y, which is x minus y the whole square. Similarly, you are invited to factor this as x plus y the whole square. That's x plus y into x plus y. The proof will be similar to the one above. So these are two expressions one must know and one must recognize whenever they appear. So here they are. Factor the following perfect square trinomials. In general, you won't be told it's a perfect square trinomial, but here we are telling you. So we are telling you that x square plus 4x plus 4 is a perfect square trinomial. What differentiates the two formulae? One is x square minus 2xy plus y square, and the other is x square plus 2xy plus y square. So what differentiates them is the middle term. Both have x square plus y square. The middle term, if it's positive, it's one trinomial. If it's negative, it's another. Here the middle term is positive. We want to express this in the form x square plus 2xy plus y square. So that tells me that the constant term 4 is y square. Let's see if it works. So I can write this as x square plus 2 into 2x plus 2 square, which is x plus 2 the whole square. The 2 takes the role of the y. So x square plus 4x plus 4 was x plus 2 the whole square. Let's see here. Here there's a minus, so I know it's going to be the minus trinomial. And 25 takes the role of y square. So let's see if I can write it. I can write it as x square minus 2 into 5 into x plus 5 square. And yes, I have it. It is of the form x square minus 2xy plus y square. So it must be x minus 5 the whole square. How do I recognize a perfect square trinomial? I take the constant term and see if it's a square. If it is, then I find out that number y, for which y square is 25, and then I test the middle term. I test if the middle term is 2 into x into y. So it is. It's 2 into 5 into x. So it works. Minus 10x is what we get. Let's see here. We have 2x square minus 12x plus 18. I'm just rearranging terms. Well, 2x square is not a perfect square, but everything is divisible by 2. So I'll pull out 2. I get x square minus 6x plus 9. So I have the x square and I have a 9 which is 3 square. So I have my y square. I need to check if the middle term matches. The middle term should be minus 2 into x into y. And it is, because this is minus 6x, which is the middle term. So it worked. So this expression is 2 common, x minus 3 the whole square. So the three main steps are identify your x square and your y square. Once you've identified your y square, which would probably be a number, then you find out y and test your middle term. is the middle term that they've provided, 2 into x into y. If the middle term doesn't match, then it's not a perfect square trinomial. Don't worry, we'll figure out ways of factoring those trinomials too, but they won't end up being a square. They won't be the same term squared. So let's look at the product of two typical binomials. So x plus 3 into x plus 2. We're just using the distributive property several times to solve this. So I get x plus 3 into x plus 3 into 2, which ends up being x square plus 3x plus 2x plus 6, which is x square plus 5x plus 6. So what's the term in x? What's the constant term? I'm going to write those down. The term in x was 5 and the constant term was 6. Let's work this out. This is x plus 5 into x minus x plus 5 into 4, which is x square plus 5x minus 4x minus 20. So that's x square plus x minus 20. Again, I'm going to write down the term in x. That's just 1x and the constant term is minus 20. Similarly here, I'll do it quickly. I'll get x square minus 8x plus 7. Please verify by multiplying it out yourself. So the term in x has a coefficient minus 8 and the constant term is 7. Similarly here, I'll get x square minus a plus bx. When I group like terms, since it's a and b, I have to keep it as a and b. I can't simplify it further. Plus ab. So the term in x is minus of a plus b and the constant term is ab. Okay, why have I listed the term in x and the constant term? Well, firstly, the coefficient of x square will always be 1 because you're just multiplying x into x, x into x, x into x, x into x. So x square doesn't give me anything exciting. The real action is because of the other term, the 3 and the 2, the 5 and the minus 4, the minus 1, minus 7. And they lead to these different terms in x and the constant terms. So look at this. This is 3 and 2, x plus 3 and x plus 2. And the term in x is 5 and the constant term is 6. So when I add 3 and 2, I get 5. And when I multiply 3 and 2, I get 6. Similarly here, the two numbers are 5 and minus 4. When I add them, I get 1. When I multiply them, I get minus 20. Similarly here, minus 1 and minus 7. When I add them, I get minus 8. When I multiply them, I get 7. Similarly here, minus a and minus b. When I add them, I get minus a minus b, which is minus of a plus b. And when I multiply minus a and minus b, I get ab. So this is the sum and this is the product of what? Of the second term of each binomial that is being multiplied. So here's the deal. If I'm multiplying x plus c and x plus d, the first term is always x, the second term are the c and d. Then the sum is going to be c plus d and the product is going to be cd. That's what I've noticed. And if you open this out, you will notice it too. So that's a very important observation because this is what is going to help us do the opposite. Given a trinomial, I will be able to factor it as a product of binomials by knowing that I'm aiming for a sum and product. So here we go, factoring the trinomial. So we're going to use what we just discovered previously and reverse the operation. Remember that when you multiply two binomials of the form x plus c, x plus d, then you got x square plus sum x plus product, where sum was the sum of c and d and product was the product of c and d. Here I'm given the sum and product, that means. So I'm given the sum is 7 and I'm given the product is 12. And I need to unravel c and d. So I need two numbers whose sum is 7, product is 12. Factor 12. 12 is 12 into 1, 6 into 2 and 4 into 3. And I'll check their sums. This sum is 13, this sum is 8, this sum is 7. I've got my sum. So I know the two numbers are 4 and 3 because 4 plus 3 is 7 and 4 into 3 is 12. So the trinomial x square plus 7x plus 12 will factor into x plus 4 into x plus 3. I have my two terms. Please check by opening this out and seeing you get this. Let's do this one. Here what do I want? Here I want a sum of minus 7 and a product of 12. I know that 4 plus 3 was 7, so minus 4 plus minus 3 will be minus 7, and minus 4 into minus 3 will be 12. So I know my two numbers are minus 4 and minus 3. So my binomial becomes x minus 4 into x minus 3. How about y square minus y minus 12? So the sum is minus 1 and the product is minus 12. So let's look at the product is minus 12. So let's factorize. I can do 12 into minus 1. I can do 6 into minus 2. I can do 4 into minus 3. But notice 4 into minus 3 is giving me a sum of 1. I want a sum of minus 1. So I can do it as minus 3 into, I can do it as minus 4 into 3. Minus 4 into 3 also gives me a product of minus 12. And now the sum is minus 1. So my two numbers are minus 4 and 3. So this factors as y minus 4 into y plus 3. How about this one? Well, firstly, there's 5 common. Let me pull it out. So it gives me 5 into 25 minus 10t plus t squared. Let me write that as 5 into t squared minus 10t plus 25. I like to write it with higher powers on the left. Now I can do sum and product. So sum is minus 10, product is 25. Product of 25 is 5 into 5. But I want a sum of minus 10, so minus 5 into minus 5 gives me a sum of minus 10. So this factors as, there's a 5 outside, t minus 5 into t minus 5. Hey, that's interesting. That's t minus 5 the whole squared. So it looks like it's a perfect square trinomial, which it indeed is. T square minus 10t plus 25 is t minus 5 the whole square. 5t minus 5 the whole square. So you see, we had a perfect square trinomial. We did not realize it was that. So we just used our sum and product method and factored it. So no big deal. The sum and product is a much more powerful tool. It will factor most things. And the last one is x square plus x plus 1/4. X square plus x plus 1/4. Fractions are a problem to deal with. So I'll just pull out the 1/4 common. So I'll take 1/4 out. I'll get 4x square plus 4x plus 1. Let's see what this is. I think this is a perfect square trinomial. I think this is 2x the whole square plus 2 into 2x into 1 plus 1 the whole square. So this is indeed a perfect square trinomial. This is of the form capital X square plus 2 into capital X into capital Y plus y square. So it is a perfect square trinomial, and this factors into x plus y the whole square. So our entire expression factors into 1/4. What's our capital X? That's 2x. What's our capital Y? That's 1. 2x plus 1 the whole square. So I noticed that 4x square plus 4x plus 1 was a perfect square trinomial because 4x square is 2x the whole square. 1 is certainly a square. And then 2 into 2x into 1 gave me the middle term 4x. And we have our factorization. So let's move on to some slightly more complicated questions. Simplify k square minus 36 into p plus 9 upon p square minus 81 into k minus 6. Well, I can see a difference of two squares in the numerator, k square minus 36. I know that k square minus 36 can be written as k square minus 6 square. So that will factor as k plus 6 into k minus 6. Similarly, I have p square minus 81 in the denominator, which can be written as p square minus 9 square, which can be factored as p plus 9 into p minus 9. So I have factorizations of some terms in the numerator and in the denominator. Let's use them and see how far we go. So this becomes k plus 6 into k minus 6 into p plus 9 upon p plus 9 into p minus 9 into k minus 6. Now we have terms common in the numerator and the denominator. So I can divide them out. K minus 6 and k minus 6 divide each other out. P plus 9 divide each other out. And I'm left with k plus 6 over p minus 9. So this is a neat simplification. Is there something missing? Yes, there is. If I am to write the original expression as this expression, since I have performed two divisions, I need to state that I was not dividing by 0. So I need to state that k minus 6 was not equal to 0, which means that k cannot equal 6. And I also need to state that p plus 9 was not equal to 0, which means p cannot equal 9. So the two expressions are equal, namely the original expression is equal to this simplified expression with the caveat that k cannot equal 6 and p cannot equal 9. Simplify xyz into open brackets 1 upon xy plus x over zy plus yz over x plus y. So all the action seems to be within the brackets. Let me simplify within the brackets. Since they are fractions which are being added, I'll take the LCM. The LCM of xy, zy and xyz is clearly xyz. So I'll write my xyz outside. I'll take xyz as the LCM. 1 over xy will become z over xyz. So the first term becomes z. The second term is x over zy. So it will become x into x over xyz. And the third term is yz over xyz, which just stays yz. So it becomes xyz z plus x square plus yz over xyz. And there we have it. We can factor out the xyz's, leaving us a 1. And the answer is z plus x square plus yz. A neater way of writing this with decreasing powers is x square plus yz plus z. If y not equal to z, then xy minus zx over z minus y is equal to. So the numerator is xy minus zx. So let me use the opposite of the distributive property. Let me take x common. So let me try to simplify xy minus zx. I see x common in both, so I pull out x and I'm left with y minus z. How do you know this is right? Just use the distributive property and you'll see that you'll get xy minus xz, which is the original expression. So the distributive property works both ways. It can be used to expand a factorization or it can be used to factor. So the numerator has become x into y minus z and the denominator is z minus y. What do I do now? I have z minus y in the denominator and I have y minus z in the numerator. So I can express z minus y again by the distributive property as minus 1 into minus z plus y. I've pulled out minus 1 common, so I'm left with minus z plus y. Quickly verify by using the distributive property. Minus 1 into minus z plus minus 1 into y will give me back z minus y, my original expression. So I can write this as x into y minus z over minus 1 into minus z plus y. But what is minus z plus y? Minus z plus y is the same as y minus z. So let me rewrite it as x into y minus z over minus 1 into y minus z. And since they've told me in the question that y is not equal to z, I can divide out the y minus z. Since y is not equal to z, y minus z cannot be equal to 0. So I'm permitted division by y minus z. And the answer I'm left with is x over minus 1, which is minus x. And that answer is E. So notice there were two steps to this question. The first step was factoring x out of the numerator to leave me with x into y minus z. But I had z minus y in the denominator. So I rewrote z minus y as minus 1 into y minus z. That's a very important step. Having expressed it as minus 1 into y minus z, I could cancel it out. And I was left with x over minus 1. A square plus b the whole square minus a square minus b the whole square. So I can expand out a square plus b the whole square. I can just multiply it out using the distributive property. Similarly, I can multiply out a square minus b the whole square. And then I can simplify like terms and I'm done. But let's do something cleverer. This is actually a difference of two squares. It's actually of the form a square minus b square. A square plus b square minus a square minus b square. So this whole thing is big A and this whole thing is big B. It is a square minus b square. So it should factor into a plus b into a minus b. So let's do that. What's A? A is a square plus b. What's b? A square minus b. The next term, A is a square plus b minus a square minus b. Whenever I have a minus, I put a bracket because the minus applies to the whole term. Now let's simplify this. This becomes 2a square. The b and minus b cancel each other. And this becomes a square plus b minus a square plus b. I'm distributing the minus 1 across a square minus b. So I get minus a square plus b. Simplifying the second term, the a squares will cancel and I'm left with 2b. So the final answer is 4a square b. That's D. If x is 3 and y is 4, then xy over 1 by x plus 1 by y is equal to. So there are two ways to go about this. You can actually substitute 3 and 4 and find out the answer. Or you can try simplifying that expression and then substitute. I'll do the latter. Xy over 1 by x plus 1 by y. I'm going to simplify the denominator. So what's the LCM? The LCM is xy and I get y plus x. So the entire expression becomes xy divided by y plus x over xy. When you divide by a fraction, it's the same as multiplying by the reciprocal. So this becomes xy times xy over y plus x, which is the same as x square y square over y plus x. Now I can substitute my values. X is 3 and y is 4. So substitute. I get 3 square into 4 square over 3 plus 4, which is 9 into 16 over 7, which is 144 over 7. The answer is D. If C is not equal to 0, then a square bc plus ab square c plus abc square upon abc is equal to, I think it should be if abc is not equal to 0, not just c not equal to 0. It should be abc not equal to 0, which is the same as saying if a not equal to 0, b not equal to 0 and c not equal to 0. That's important. So the numerator has ABCs raised to various powers. But what's common to all the terms in the numerator? Every term has A, B and C. So using the distributive property, I'll pull out ABC common. What's left in the first term? Just an A. In the second term, just a B. In the third term, just a C. Should we confirm that? Let's use the distributive property and check. So this becomes ABC into A plus ABC into B plus ABC into C, which becomes A square BC plus AB square C plus ABC square, which is our original numerator. So this factorization was correct. pulling out ABC worked. So the entire expression becomes ABC into A plus B plus C upon ABC. Notice that to cancel out ABC, I need to have all three of them not equal to 0. Just having C not equal to 0 doesn't do it. So since A and B and C are not 0, I can divide them out and I'm left with A plus B plus C. That's the answer, A. The expression 3 over x minus 1 minus 6 will equal 0 when x equals which of the following? 3 over x minus 1 minus 6 should equal 0. When will it equal 0? Let's understand it. You have some weird expression, minus 6 equal to 0. Well, obviously when you're subtracting 6 to get 0, this weird expression should equal 6. So I want 3 over x minus 1 to equal 6. 3 divided by something should give 6. So obviously that something should be half. 3 divided by half is 6. 3 divided by half is equal to 6. So I want the denominator to be half. So I want x minus 1 to equal half. So I want x to equal 1 plus half, which is 3 by 2. The answer is D. If you find solving this equation complicated, just substitute values one by one and something will work. Simplify. 1. R square raised to 4 plus R cube into R square upon R raised to 5. Recall your laws of exponents. A power raised to a power, you multiply the powers. So R square raised to 4 plus R cube R square will become R raised to 2 times 4 plus, what happens when you multiply two powers, R cube times R square? Then you add the exponents because finally you will have 5 R's being multiplied. So it's R raised to 3 plus 2, which becomes R raised to 8 plus R raised to 5. So I write down the entire expression. The numerator became R raised to 8 plus R raised to 5 upon R raised to 5. Now we know what we can factor out from the numerator. We can factor out the entire R raised to 5. What's left is R raised to 3 plus 1. Confirm, multiply it back in and see if you get the original expression. R raised to 5 into R raised to 3 is R raised to 8. R raised to 5 into 1 is R raised to 5. So you do get the original expression. So this becomes R raised to 5, R raised to 3 plus 1 over R raised to 5. I can cancel out the R raised to 5. I'm left with R raised to 3 plus 1. That's my answer. What about part 2? R raised to minus 2 into R raised to 5 over R square raised to minus 5. Since I'm multiplying two powers, I add the exponents. I get R raised to minus 2 plus 5, which is R raised to 3. Denominator, since I'm raising a power to a power, I multiply the exponents. 2 times minus 5, which is equal to R raised to minus 10. So I have R raised to 3 upon R raised to minus 10. What do I do to exponents when I divide? I subtract them. So this becomes R raised to 3 minus 10, which is R raised to 13. So that's my answer. Simplify. Root x minus 3 upon root x plus 3. X not equal to 9. Okay, this is a very important question. This technique needs to be learned. So when I have a root sign in the denominator, I want to get rid of it. So what's the best way to get rid of a term of the form root x plus 3? When I say get rid of, I mean simplify it. I should multiply it by root x minus 3. Because then I can use the difference of two squares. And this is a plus b into a minus b, which will become a square minus b square. So it will become root x squared minus 3 square. And that's what I wanted. I wanted to get rid of the root x. And root x squared is nothing but x. So it becomes x minus 9. So this is a very important step. If you see roots and you want to get rid of them, you end up using the difference of two squares so that the roots get squared and you're left with a much better expression. So what I'm going to do formally, since this is the question, I'm going to multiply the numerator and the denominator, of course, by the same expression. So I'm going to multiply the numerator and the denominator by root x minus 3. Since I had a root x plus 3, I multiply by a root x minus 3 so that I can use my difference of two squares formula. Let's see what this becomes. The numerator is just root x minus 3 the whole square. And the denominator, as we saw, is a plus b into a minus b. So that becomes x minus 9. So let me further simplify the numerator. That's a perfect square trinomial. So that becomes root x square minus 2 into root x into 3 plus 3 square upon x minus 9. This becomes root x square, which is x, minus 6 root x plus 9 over x minus 9. And this is my answer. Why is this a simplification? It's actually a matter of taste. It's a simplification because the denominator does not have any root signs. The denominator is now clean. It's x minus 9. One can argue that the numerator is more complicated. True, but it's the denominator that's become clean, and we often do that. We like to keep the denominators clean because when we add and subtract, we need to take LCMs, and it's nice to have neat denominators.